Let us learn about a few fully controlled power semiconductor switches. Three fully controlled power semiconductor switches are shown here. Bipolar junction transistor, NPN bipolar junction transistor, and we have a MOSFET, and MOSFET stands for metal oxide semiconductor field effect transistor, and IGBT, which stands for insulated gate bipolar transistor. Among these three, MOSFET and IGBT are very widely used in many power electronics applications. BJT is brought here for easy comparison. Power BJTs are not very popularly used. In fact, they are no longer manufactured also at significant voltage and current levels. But MOSFETs and IGBTs are being manufactured in large scale at different voltages and current levels. Again, in BJTs, they can be PNP or NPN. Here an NPN BJT is shown and its circuit symbol is also shown. BJT is a 3-terminal device. It has collector, emitter and base, 3 terminals, and base is the control terminal. So if you inject some base current, the collector current will flow. That is how the device conducts. NPN BJTs are more popular in power applications, were more popular in power applications. And MOSFETs, there are different kinds of MOSFETs. There are enhancement mode and depletion mode. The enhancement mode MOSFETs are normally off MOSFETs, which are used in power electronic circuits. And there are N-channel MOSFETs and P-channel MOSFETs. Again, in power electronic circuits, the actual type of MOSFET that is used is, it's an N-channel enhancement mode metal oxide semiconductor field effect transistor, N-channel MOSFET. MOSFET is again a 3-terminal device. It has gate, drain and source. 3 terminals, and gate is the control terminal and drain and source are the power terminals. For example, if you imagine a switch like this, see, we are looking for the realistic replacements for this ideal switch we have been drawing so far. So 2 terminals, that means the voltage or the current flows through these terminals when the switch is on in this direction. The voltage is blocked across these terminals in this direction or the other polarity. So these terminals are known as power terminals, where the current flows or through the terminals through which the current flows when the device is on. But to command the switch to turn on or turn off, we need another terminal that is called control terminal. So the third terminal is control terminal. It is gate in the case of MOSFET and it is base in the case of BJT. IGBT is also a 3-terminal device. It has collector, emitter as the power terminals and gate is the control terminal. Let us quickly compare the structures of these 3 devices. One common thing that is present in all the 3 devices is the N- region. N- region, that is known as the drift region. As already mentioned in the discussion on diodes, this N- region is known as drift region and it is present in almost all power semiconductor devices, and the width of the drift region, N- region, decides the voltage blocking capability of the switch. Please recall that the voltage is always opposed. The external voltage applied in off state of a switch is always opposed by an electric field across a PN junction in most of the power electronic semiconductor devices, power semiconductor devices. For example, the voltage is blocked by this PN junction in BJT primarily, and this PN junction in MOSFET, again this PN junction, PN- junction. in IGBT. And there is another difference in these structures, among these structures. The control terminal which is base, it is directly connected to the device. It is directly connected to the device through a metallic contact, like the other power terminals. Like for example, collector is connected to this whole region through a metallic contact. Metallic contacts are basically needed to bring out the terminals. We have a block of semiconductor and we need to package it and bring out the terminals so that it can be connected to the external circuit. So in the case of BJT, all the terminals, the power terminals and the control terminal, are connected to the semiconductor device through metallic contacts. This blue color is metallic contact. Whereas in MOSFET and IGBT, the control terminal, which is gate, it is not directly connected, or which is not electrically connected through a metallic contact to the semiconductor block. In fact, there is a dielectric material which is usually the oxide. That is why this name metal oxide semiconductor. So silicon dioxide is one of the dielectrics that is used. The control terminal is insulated. That means we have a metallic contact and then we have the semiconductor block. In between there can be a dielectric, there is a dielectric material. So the control terminal is insulated. That is why the term insulated comes in the name of IGBT. So this metallic surface, and we have a semiconductor surface which could be conducting, and in between a dielectric. So this brings in the effect of capacitance between the control terminal and the device. For example, you can expect to have a capacitance between the gate and source, because source is connected to this p-type region which is here. So and gate is this. So you can expect a capacitance between gate to source in a MOSFET. Similarly, you can also expect a capacitance between the gate and emitter. And how does the conduction happen? The conduction happens due to flow of electrons and holes in a BJT and also in an IGBT, but the conduction happens primarily due to flow of electrons in MOSFET. So BJT is a minority carrier device because we have minority carriers on either side when the device is conducting, and IGBT is also a minority carrier device. We will see how is it a minority carrier device. And MOSFET is a majority carrier device where only one type of charge carriers take part in conduction. And how does the conduction happen in a MOSFET? It is illustrated here. So for example, when you apply a positive voltage at gate with respect to source, so when VGS is positive, due to the electric field created by this positive potential that you have applied, the electrons in p-type, electrons in this p-type region, this is known as substrate. So electrons in p-type region, which are minority carriers, they are attracted towards the boundary and a channel of electrons, this channel of electrons is formed. So this is channel of electrons. So as long as this VGS is positive, there is a channel through which electrons can flow. So electrons can start flowing from source to drain as shown. Because once you cross this channel, everything else is n type only. It's n minus, this is n minus, this is also n plus. So it's all n type. So conduction can easily happen. And similarly in the other part of the device. So the point to note here is that electrons can flow either way. They can also from drain to source or source to drain, because the channel is just a path to facilitate the flow of electrons. Another interesting thing is this body diode. What is this body diode in a MOSFET? If you observe the structure, this p-type region is directly connected to the source terminal, and this n-type region is connected to the drain terminal, and in between of course there is an n- region. So you have a direct connection of PN junction from source to drain. So from source to drain you can imagine that as a diode. So this is known as body diode, which is always present in a MOSFET just because of the way it is constructed. So conduction in reverse direction, that means flow of current from source to drain, can happen in two ways in a MOSFET. It can happen through the body diode, which is a PN junction, or it can also happen through the channel. So which path will the current take? It will take the path of lower resistance. But of course this conduction through channel can happen only if the gate to source voltage is positive. Now look at the IGBT. When you look at the IGBT, based on the structure, the IGBT can be seen as a MOSFET driving a PNP BJT. See, this is an extra P plus region that comes above the N plus region if you compare the structure of MOSFET. So we have a P plus on top of this N plus, and we have an N- region which is the drift region, and there is a P-type substrate. So we have a PNP transistor. So P, N, N minus P. So this whole thing is a PNP transistor, and then the base of the transistor can be fed if this channel is activated, can be fed by current, can be fed with current if this channel is activated, and that activation is done by applying a positive voltage across gate and emitter. So when you apply a positive voltage across gate and emitter, a channel of electrons is formed. So electrons can flow from emitter to this N- region, which is the base of this PNP transistor. So the current conduction can happen from collector to emitter. Please note that the PNP transistor that we are referring to is an internal thing. So its emitter is E prime and its collector is C prime, but the main collector terminal of IGBT is actually the emitter of the internal PNP BJT. Okay, so that is why the current will flow in this direction. So as we all know, a BJT can not conduct in reverse direction. So that is what is mentioned here. It can conduct only in one direction. Collector to emitter, the current can flow. Current flow can happen in this direction. Why? Because the base is thin and lightly doped, emitter is heavily doped, and collector is moderately doped in a BJT. And the base emitter junction should be forward biased. The base emitter junction should be forward biased for conduction. So it can only happen in one way because it's again a PN junction. That is why current conduction is unidirectional in BJT. Whereas in MOSFET, as we have already discussed, current can conduct in both directions. With positive VGS, electrons can flow from drain to source or source to drain, taking the path that was described earlier. When it comes to IGBT, it can only conduct in one direction because this PNP transistor, the PNP transistor that is internal to the IGBT, can only conduct in one direction. So among these three devices, MOSFET has bidirectional current carrying capability. That is the point to note. And how about the voltage blocking capability? A BJT can block only positive VCE, significant positive VCE. Because of the structure and the doping concentrations involved. For example, base is thin and lightly doped. Emitter is heavily doped. So this base emitter junction, since emitter is heavily doped, this base emitter junction, this junction, it breaks down at very low negative voltages. We all know that when we have a PN structure like this, PN structure, we know that voltage in this direction can be blocked. So intuitively, when we have an NPN, we tend to think that okay, positive voltage can be blocked by this junction because it's the other way, and anyway negative voltage can be blocked by this junction. So we tend to think that this switch, this NPN device, can block in either direction. Theoretically it is correct, but because of the doping concentrations involved, because the doping concentrations are essential for the circuit operation, the conduction of BJT is because of the fact that the base is lightly doped and very thin. So because of that, and the emitter also has to be heavily doped for the BJT to conduct. So because of that, the base emitter junction will have lesser voltage blocking capability. In fact, it will be negligible when compared to the other collector base junction. So that is why BJT can block voltage in only one direction, that is positive VCE can only be blocked by BJT. So this is a very interesting point to note. So far, if you think that we are replacing this switch with a diode, for example, this is our switch, this is terminal X and this is terminal Y, and let us say we imagine that a diode comes in the place of the switch. Then what we have known that when current flows, it flows in this direction, and when the diode is in off state, the voltage across the diode, this is negative. But here in the case of BJT, if you look at the current direction, when the current flows, it flows from X to Y. Again, imagine X to be collector and Y to be emitter. When current flows, it flows from X to Y. When the device is off, the voltage between X and Y has to be positive for the device to stay in off state. It cannot be negative. How about the voltage blocking capability of MOSFET? It is obvious, because of the body diode, MOSFET can only block positive voltage across drain and source, because the diode is connected in the other way. Because when VDS is negative, body diode will easily conduct. So the device can only block in one direction, but it can conduct in either direction, as we have discussed. And how about IGBT? Again, going by the same intuition, let us say you have a PN structure. This IGBT has PN kind of structure. We tend to think that it can block voltage in either way, because there are three junctions, two of them will oppose positive voltage and two of them can oppose negative voltage. We can say that it can block in both directions. Yes, theoretically it is true, but in practice, because of various device design trade-offs, this P-type and N-type regions, they have to be heavily doped, this P plus and N plus. So the reverse blocking capability, it depends on the breakdown voltage of this P plus N plus junction. So it's not always true that if a IGBT is blocking 1000 volts in one direction, it will also be able to block 1000 volts in the other direction. Theoretically, it seems that it should be true, but it is not so in reality. So here are the idealized VI characteristics of these three switches: ideal BJT, ideal MOSFET, and ideal IGBT. So ideal BJT can conduct in only positive direction. So IC can be positive, the collector current, and VCE can only be positive in the off state. Whereas ideal MOSFET, the drain current ID can be either positive or negative in the on state, but VDS, the voltage between drain and source, when the device is off, can only be in the positive side. IGBT, theoretically yes, VCE can be in either direction when it is in off state, but usually it is limited. In fact, it cannot extend further, it is limited. But the collector current is definitely unidirectional, it cannot conduct in the reverse direction. How do the actual characteristics look like? They look like this. So in the off state of a BJT, off state corresponds to a point on this x-axis, a point on this x-axis. It depends on the voltage that is appearing, and that depends on the external circuit conditions in which this BJT is connected. And how does the conduction start? The conduction starts by pumping a base current. So the device will be in off state and blocking VCE when IB is equal to 0. And when we increase base currents like IB1, IB2, IB3 and so on, the device can carry more and more currents. And where is the on state located? The on state is again a point on this line. In fact, in power electronic circuits, a BJT is never operated in this region because of the fact that if we look at one point here, it shows that the voltage across a device is more for the same current. So it causes more conduction loss. So the on state of a BJT corresponds to a point on this line only, BJT is a current controlled device because you need to maintain certain base current for a particular collector current to flow. Whereas MOSFET is a voltage controlled device, and even IGBT is also a voltage controlled device. So we need to impress a certain voltage across gate and source and or gate and emitter for the device to stay conducting. And the current that the device can carry depends on the amount of VGS, that you are impressing. Please note, the amount of VGS or VGE decides the current that the device can carry, but the actual current that the device is carrying depends upon the circuit. For example, you have a circuit connected like this. Obviously, the current that is flowing through the device will be decided by this voltage source and resistance. By impressing a certain value of VGS, we are ensuring that the device can carry that much current if an external circuit tries to push. That is how we have to understand these curves. So again, in the MOSFET, on state corresponds to a point on this line only. It is never operated in this saturation kind of region. As we have discussed, the on state could also be a point in the third quadrant because the device can carry in the current in the negative direction. But again, the point of operation, the actual operating point, depends on whether the channel is connecting or whether the body diode is connecting. And the device will be in off state if VGS, the gate to source voltage, is less than certain threshold voltage known as VGS threshold. Okay. So MOSFET is a voltage control device, so is IGBT, and again IGBT will be in off state when VGE, the gate to emitter voltage, is less than VGE threshold voltage, VGE threshold. Again, in the case of IGBT, the on state is a point here and off state is a point here. It could also be a point in the negative direction, but then this voltage blocking capability in the reverse direction is very limited, as we have discussed earlier. When the MOSFET is conducting, it can be represented by this equation, ID into RDS on. It's in the on state. So because the operating point is just lying on the straight line and the slope of the straight line, in fact the inverse of the slope here, is the RDS on. What is RDS on? The resistance between drain and source of a MOSFET when it is in on state. This is a very important parameter and it is mentioned by the manufacturers, and in fact often the MOSFETs are selected based on this RDS on. So if you have two MOSFETs with the same voltage and current ratings, one would immediately choose the one with lesser RDS on because it's going to give him lesser conduction loss. Whereas in IGBT, you have a minimum voltage that gets dropped when it is on. So VCE in the on state can be written as VCE naught plus some IC into some RCE. It is just like the diode characteristic, where RCE is the inverse of the slope of this straight line region. This is the on state of IGBT. However, these actual VA characteristics will be used for loss calculations mostly, and as far as the circuit analysis is concerned, the ideal VA characteristics are used. Another point to note is the control effort. For example, let us say you have a on state, off state, on state like this for a given switch. So the base current needs to be present. For example, if the switch has to be on here, off here, again on here, base current has to be positive as long as the BJT is conducting, and it could be 0 or negative for a quick turn off. For example, one can apply a negative base current and then the device is turned off quickly. But again, if the device has to be turned on, you have to apply a positive base current. So always current flows into the control circuit, the control terminal part of it, control terminal part of the device. So power is consumed by the device even when it is on through the control terminals, that is what is control effort. Whereas in the case of MOSFET, this is isolated. This gate is isolated. That is why you don't see a connection. Even in the symbol, you don't see a connection between the control terminal and the power terminals, any of the power terminals. Same is the case with IGBT. See, there are two lines which are not together. So that is also represented in the circuit symbol. So what do we have? We have a capacitor. We have a capacitor effect between gate and emitter in an IGBT and between gate and source in a MOSFET. So what do you mean by the device turning on? The device turning on means that this capacitance is getting charged. So the currents, the gate currents in this case, the control circuit currents will be like this. So once the device is commanded to turn on, current is drawn through this gate terminal to charge this capacitance. So in fact, if you have a pulse generator, something like this, one will definitely have a resistance in the gate circuit. So this is gate and we have some gate to source capacitance. So to limit the current in this circuit, a resistance is kept. This is usually known as the gate resistance. So what will happen? Once the capacitor is charged, that means the device is fully on, no current or insignificant amount of current is drawn from the gate terminal. So this is on now, fully on. And then in the off state, of course, there is no current. Again in the on state, only little current is drawn. So the control effort is less control effort in the case of MOSFET and IGBT. What do you mean by control effort? Power drawn through the control terminal is what, or the energy consumed by the control terminal is much less in the case of MOSFET and IGBT, while it is significant in the case of BJT. This is also another reason why BJT is not so popular these days, especially after the significant advances that have happened in MOSFETs and IGBTs. Here are some real examples of these switches. MOSFETs and IGBTs, they are primarily available as discrete switches and modules. Discrete switch means it's a single switch. Modules means two switches can be clubbed together, and or 4 can be clubbed together, or 6 can be clubbed together. And there are also hybrid switches, which we'll shortly see what they are. There could also be a combination of a switch plus diode in the same module. And the modules are typically screw terminal devices. So you connect to these terminals through lugs and screws, wire lugs and screws, or bus bars can be connected to this through screws. Whereas the single switches, discrete switches, are mostly printed circuit board components. It could be surface mount component, or it could be a through hole component. Again, in through hole there are two very popular packages, TO220 or TO247 package, which are illustrated here. And the surface mount package, TO263 or D2 pack, is the most popular surface mount package. These are not all the packages that in which the switches are available. There are many other packages which are very specialized for a particular application also. But what illustrated here are the most popular packages. And here are some example ratings of MOSFETs. The MOSFETs are primarily manufactured using 3 semiconductor materials: silicon, silicon carbide and gallium nitride. Whereas IGBTs are manufactured only using silicon at this moment. And a typical examples of ratings, MOSFET ratings in discrete, for example, discrete silicon MOSFETs are available up to some 900 volts and about 100 amperes of current, because beyond that it is difficult to be handled by PCBs. Even 100 ampere is a big challenge to be handled by a PCB. Whereas if you go for a silicon carbide MOSFET, you can have devices, MOSFETs, which can block higher voltages and higher currents. Again, gallium nitride MOSFETs right now are available at low voltages, relatively low, about say a few hundreds of volts, and they are available up to a few tens of amperes of current. But more advancements are happening, and we expect to see much GaN devices of much larger voltage ratings in future. IGBT is the most popular semiconductor device used at high voltages. So they are available all the way up to the ratings of like 6.5 kV and a few hundreds of ampere, like 750 ampere or so. But you see that there is some overlap in the ratings. For example, you take the 1200 volt range. See, 1200 volt, you have an option to go with this, or you have an option to go with a silicon IGBT, right? So it depends on the performance. Now, what is the performance? The performance is basically, we are looking at a switch, so we want it to consume as less power as possible. We want it to switch as fast as possible. So people will look at the conduction loss and switching loss. And how are they characterized? The conduction loss is characterized by the voltage drop that occurs in a device when it is on, and the switching loss is characterized by the speed at which the device can switch. MOSFETs can switch much faster than IGBTs. They can switch within a few nanoseconds, and they could take up to a few tens of nanoseconds to switch, to turn on or turn off. Whereas IGBTs, the low current IGBTs could take few tens of nanoseconds to switch, but typically few hundreds of nanoseconds are required for an IGBT to turn on or turn off, and it can go all the way up to a few microseconds when you go to very high current IGBTs, like thousands of volts and thousands of amperes are being blocked and conducted. And since the MOSFET can switch faster, it can be used in high switching frequency applications, and IGBTs are used typically in low switching frequency applications. Depending on the switching transition times, you can only switch, you can only turn on or turn off a finite number of times in a given second. That is what is meant by the switching frequency. Let us try to understand hybrid switches which are used in power electronic circuits. In fact, they are needed to achieve or to realize certain circuit topologies. Let us say we have an IGBT whose negative voltage blocking is negligible. So an IGBT, as we have discussed, it can only block positive voltage, it can only conduct positive current, it can block either way, but the device has been designed such that it can only block in one direction. Let us assume that. Let us take a diode. We know that if you write a diode like this, it can also block in the same direction as indicated, voltage plus V. When V is positive, it can be blocked by this diode or this IGBT. But the IGBT can conduct only in one direction. The diode can connect in the other direction when it is on. So if you join these two devices, like this, now you will have a new device, a new switch, which can conduct in either direction but block only in one direction. So when you connect a diode, anti-parallel diode with an IGBT, it can facilitate conduction in both directions, current conduction in both directions, and both the IGBT and diode can block in the positive voltage. So that is what is represented by this second figure, VI characteristic. The limitations, for example, the red color limitation is shown because of the device ratings. So you cannot have infinite voltage blocking capability and all that. Realistic device will have some limitations. This red color region, the red color boundary illustrates that, and the green color hatched region depicts the operating point. So the operating point can be anywhere within that region. So the device can be conducting any current, okay, or it can be blocking any voltage. Now when you connect two of them in an appropriate manner, so for example you flip this combination of IGBT and diode and connect it with the original one in the third figure, third rightmost figure, we can say that this particular device can block voltage in either direction. You have two diodes connected, so this diode can block voltage in this direction, this diode can block voltage in this direction, and same is the case with this IGBT. And current conduction can happen through this IGBT and this diode. Sorry, this is how it should be. And current conduction can happen through this IGBT and this diode. So if you have a power electronic circuit, and in that circuit you have two terminals X and Y, between which a switch needs to be inserted. So you need to look at the current carrying capability of the switch and the voltage blocking capability of the switch. If the switch needs to carry current only in one direction when it is on, and if the voltage blocking capability or the polarity of the voltage that needs to be blocked by the switch when it is off is consistent with this IGBT, one can go ahead with the first option. But the voltage blocking capability is the same, current needs to be bidirectional, then one has to go with the second option. Why? Because the diode being connected in anti-parallel direction will allow current flow in the reverse direction, but it will also block voltage in the same direction. But let us say you have a switch in a power electronic circuit which needs to block voltage with either polarity and conduct in either direction, then you need to go for a third kind of switch. So the dimmer circuit that we have seen is an example of this. So you have an AC source connected to a resistor. So the switch has to conduct current in either direction, and the switch also has to block voltage in either direction, because we will be turning off the switch whenever we want. That is what we have seen in our example. that is an example of a switch which needs bidirectional voltage blocking capability and bidirectional current carrying capability. So this is how different hybrid switches can be realized in power electronic circuits and employed in a particular application according to the need.